Welcome back to HVAC-Engineering-Techie channel. This is a channel where we talk all things HVAC. We talk about engineering design, construction, equipment, systems, test and balance extensively, controls, efficiency, and system performance. These videos are intended to be educational in nature, to help you with your career, to advance your career, and of course it'll help you on the job. Today's lesson is on the test and balance of exhaust systems. It's a short video, but it does have some interesting things that make exhaust fans different than a regular supply air system. So before we do that, I'd like to thank you for being a subscriber to the channel. If you're not, boy, I'd really appreciate if you do that. Hit the subscribe button down below and give me a thumbs up if you like it. And the reason is Google uses that data to evaluate this channel. Now, to become a subscriber, it's absolutely free, costs you nothing. It's super simple for you, but it's really, really helpful to me. So if you do that, I'd really appreciate it. And then, of course, you'll be able to always view all the other videos, which is fairly extensive, and hopefully this will be helpful to you. So let's go ahead and get started on talking about exhaust fans. Okay, let's talk about exhaust fan systems. So why are exhaust fans different than regular systems for balance? How are they different than regular system? Well, the main problem is that when an exhaust fan duct leaks, it actually means the fan has to be large enough to include that leakage. The fans, the CFM from space, plus the leakage it has to be. So I always make sure that on a job, if I'm doing a design review, that the designer has included enough CFM shoulder area so that we can raise the fan up to actually do the job. So this is just a simple exhaust fan. The grills total 1,200, and its leakage is 12%, which is real reasonable. 144, so it means the fan must really be able to do 1,384, not 1,200. And sometimes designers never think about that. When I was a designer, I would have never thought about it. In life, you learn things as you go along. So this is something we have to take into account for, that they have enough shoulder area. They may be constant volume or VAV volume, depending on the application. Measuring exhaust fan flow may be challenging because this may all be hard to get to. Typical exhaust fan systems are restroom exhaust, general area exhaust, fume hood exhaust, area relief fans, kitchen exhaust, laboratory exhaust, biohood exhaust, smoke control exhaust, stair air pressurization or area pressurization fans for life safety, and egress. Also, there's another one I didn't put on here, but that's basically return fans. If you have a separate return fan, it might be an inline blower or something like that. Balance and exhaust fans. Okay, so this is like an inline blower, and basically what you want to do is you need to read your static reading right at the discharge of the fan and right at the inlet of the fan in the cabinet, because you want to read the fan curve. So you need to be pressure across that fan. You can't have any device between this location you take the pressure and the fan discharge. Now you got to understand that this fan is going to be a jet right out of there, but for static pressure readings it doesn't really matter, as long as you're not trying to read right on the edge. So exhaust fan readings, normally you can't get to this part right here to take a pitot to tell flow, and you can't use you can't do the total of the grills here if you have to, but you can also pitot the ducts as they come out. You may have to do 2 or 3 pitots and add them together. Of course, the static pressure is in this inlet plenum and the outlet, which is 0. Methods of finding flow, pitot readings, normally hard to find to get a clear space on them. Total of all grills, duct leakage not included. And remember, that's you'll raise the fan up to where the room CFM are correct, but now you really don't know what the fan is unless you pitot it. Fan curve, we can, but unfortunately these may not be as accurate as always, least accurate in the process. So how do we balance the exhaust fan? The pitots need to be laminar flow, and that means you got to have enough entrance space, and normally we say 4 to 6 diameters before the pitot and at least 2 after the pitot. And this is a nice straight duct. This would work great. Don't always look this way, so they may look this way, and you may have to take pitots over both sides or more than one duct and add it together to get your reading. And of course, the pressure reading would be inlet and outlet would be 0. Need to take motor RPM and volts and amps, fan curves. So you can, from motor RPM, volts and amps, and the pressures, you can get your readings on the fan curves. This is utility sets. Utility sets are basically centrifugal fans, normally roof mounted or in a fan room or something. And of course, you can get your static readings, inlet and outlet right there. This is easy to do, and you can get a pitot. And these normally pitot are pretty good, especially if they're round duct. They'll pitot pretty good, but you still remember you need 4 to 6 diameters upstream, 2 diameters downstream. If you don't have that, then you don't have laminar flow. Then you've got the pressure reading. You're going to do motors, RPMs, volts, and amps, and try to take it off the fan curve. And you can always get good pressure readings here, so you're probably pretty good with the fan curve here. This is a box fan, which is normally a centrifugal fan in a box. Can be a propeller fan, but the propeller fans are real small ones, and they don't do much of anything anyway. So the box fan basically gets your pressures right across the fan very easily. And again, the pitot, 4 to 6 diameters upstream, 2 diameters downstream. And that should be pretty good. So box fans, again, the pitots, pressure readings, motor RPM, volts and amps, and the fan curve. And a fan curve for a box fan should be pretty good. All right, propeller fans are problematic, but propeller fans, if they're small, like a 12 by 12 or 18 by 18, you can actually stick a hood on it. That works pretty good. If they're bigger fans, you can use a Velgrid or a Velgrid discharge, or use a rotating vane anemometer. They work pretty good for these fans. You can do a duct pitot if they have a duct on them, and some of the fans that are used for garage exhausts do have ducts on them, so you can do a pitot. Fan RPM, motor volts and amps, fan curves. So this is not too hard to take readings on. Static pressure, again, is 0 for the inlet pressure and whatever pressure on the duct. And if it's a fan without a duct, you can't really do pressure. So you basically have to figure out another way. So balancing laboratory hood exhaust systems. These are more complex, and we'll get into this a little bit. Pressure control systems. What's important about these is normally, because they're biohoods, what's in the hood is not too safe. So they want to make sure it gets proper dilution. So they have velocity stacks that they're normally trying to shoot this air at least 20 feet in the air above the stack. And they want to get it away from any people who might be on the roof and get it to dilute up in the air. So that it's really important that the velocity remain constant. So what they do is they put a velocity sensor in the stack that actually runs the fan speed. So it guarantees that we'll always have design velocity on this stack. And then what they do is we have the exhaust system coming in here, and these are normally variable volume because the hood sashes go up and down. And then what they do is, so that I'll go on and do it. I'll get ahead of my notes here. The dilution damper modulates controlled duct pressure from overpressure. So it's got a duct pressure here sensing this, and these are normally 2, 3, 4 inches, normally fairly high static. And when you balance this, you set it up so that this stack velocity will give you that negative pressure that you actually need and handle the flow of the system. And then what happens is if this gets too high, it opens this dilution damper, it modulates it, and it allows other air in so this stack velocity can stay constant. Remember, it has to stay constant. Even if this goes down, it opens it up somewhere else. Get it? Now, as a control contractor, these are problematic and get them not to hunt. It's hard. So basically, these may hunt just a tiny bit, but it's hard to do because the speed of the damper has to be really slow, and because it's trying to chase pressure. Take pitot readings for flow. So basically, you're going to pitot the ducts to tell what flow you're at, and then you're going to take pressure readings across a filter and across a unit. So basically, we have here for the fans, and then we have a filter flow, so we know what the flow of the filter is with the clean filters. We can check that also. The motor RPM is volt and amps. So here's the sequence for these units. The unit shall be enabled anytime the lab is in the occupied mode. Fan speed shall be controlled to maintain stack velocity set point. The stack velocity set point should be set to maintain the duct negative pressure required for the lab hoods and the injection velocity. The duct pressure sensor shall modulate the dilution damper to prevent duct high pressure. Monitor fan status, speed, duct pressure, and dilution damper position. That's basically how these systems work. So how do you balance them? They're not terribly difficult to figure out how to balance, but normally there's a lot involved because it's a very serious system. Going to test the fan of the VFD to make sure it works and is ready to run. Set the fan and exhaust hoods for maximum flow. So we're going to go out here in the space and make sure the hood sashes are up and we're at maximum flow. Establish the exhaust duct static pressure set point to achieve design flow at the exhaust hoods and program it into the dilution damper control system. So we have a control system running this, and you're going to program what the static pressure needs to be for all those hoods to have flow. Establish a stack velocity set point to achieve design maximum flow in the exhaust duct with the dilution damper closed. Program this set point into the VFD stack velocity control. Normally stack velocity is set to establish plume is ejected 20 feet above, like I said before. That test the dilution damper for proper operation by changing the flow to several exhaust hoods to vary the exhaust flow and vary the dilution damper modulates to allow the exhaust fan a constant flow of air. Control operation should be very slow due to pressure control quick response. Record exhaust duct pressure set point, exhaust stack velocity set point, maximum exhaust airflows, and the motor speed and voltage amps. So this is really kind of an important thing to do, but it does allow to balance, and as long as they're set up like this, they will work correctly. You don't need to balance the dilution damper flow. You just need to balance this side and balance this side, and then the control's job is to make them work together. So we don't care whether the air is coming in here or coming in here. It really does not apply to the balance. Kitchen systems is another important one. I have a bad habit of going to a restaurant. The first thing I do is I walk in the front door to figure out which way the air is going. Is it hitting me in the face or is it hitting me in the back of the head? And of course, normally hitting you in the back of the head because the exhaust hoods are not set up correctly and they're drawing most of their air from the dining room, which is not correct. And now the dining room's under negative pressure, which is what we don't want. But one of the important things is right here. This is normally restaurants are set up where they have a food area where they prep the meal. You know, the cooks are one thing cooking it, but there's someone else that plates it, makes sure it's on the plate. And they need to make sure that there's not enough air moving across that plate to make it cool. You know, they'll normally have heat lamps above that area to keep the plates of food hot. So we have to worry about that a bit. So we have an exhaust system here, which has grease filters in the unit, comes up and goes to utility set or an outblast exhaust fan. And then we have to get air into that to make up for it. So we can put a unit in the space, a makeup air unit that blows air to make up for this hood. And for design, the rule of thumb is to make up no more than 80% and take 20% from the dining room and give 80% to the kitchen area. Now, the problem here is you have the chefs and cooks working in the kitchen, and this needs to be able to provide some cool air. If not, they're going to get hot and they're going to turn them off. That's the problem. You know, if you're in a humid area and this is an evap cool type thing, it won't do any good. So if you got a humid space, this needs to be an air conditioner. Now the problem is, again, it's bringing in 100% outsider to make this up. So there are different makeup sources. You can make up directly into the kitchen space, like I just said, or you can make up in a push-pull hood. In a push-pull hood, we may have a makeup air unit, and this can be an evap cool because it's not going to the space. It's going to this outer shell of the hood. And really we have two hoods. We have an inner hood that has a grease, and then we have these outer hood, which has louvers down here in the face of the grill. And so this makeup air unit blows in it, and it blows down to be entrained back against the food. So then it is kind of important how this works. Some chefs prefer ones that have large area of perforated metal so that the air is very slow velocity and just kind of come out into space. It'll come out like this, be sucked back in. Some prefer that they have louvers here, regular grill louvers, so they can direct the air where they want. And there's always a decision. Do you want the cooks to be in this stream or do you want the food to be in the stream? So that's important what they decide how they're going to push-pull it. You can also take it through the space from the restaurant However, it's only recommended you do about 20% from the restaurant. The rest be from some kind of makeup system. The problem with makeup air systems is high ambient. It gets very hot on the roof, and if you get this hot air across an air conditioner, it may not survive. Difficulty for AC equipment, better for evaporator cooled, but again, if you have a high humid evap, they don't do anything. So how do you test and balance these? Test the exhaust fan and makeup air unit for operability. Balance the exhaust fan for design exhaust flow. Key characteristic is capture velocity at the hood. Flow may be determined from a pitot of the main duct exhaust, Velgrid of the grease filters, and verify reading from the fan curve. Those are the three things you have to do. Velgrid can be done here. It's not too bad when you do this. And this hood may be a single side or maybe dual side, whichever, or you can just pitot the duct, either one. The problem with pitot in this duct, it may be a welded duct. It probably will be a welded duct. And so you can't use plastic plugs in a welded duct. It'll have to have a cap pitot plug that's designed for steel. Okay, so balance the system by 80% flow of the hood. 20% variance is taken for the kitchen and dining room to establish proper pressure flow. Verify that makeup air does not blow directly on the cooking surface because it will cool the food. So you can't blow it down on the hood itself. Record exhaust fan flow, duct inlet pressure and outlet pressure, and fan motor speed, volts and amps. One time I had a problem when I had a kitchen. It was a restaurant. And unbeknownst to me, it had a push-pull hood. The filter was incorrectly installed in the unit. I was the mechanical contractor. And it had about an inch open above the filter. We had to safe it off. But at the time, when the restaurant opened, we didn't have that safed. And there was a gnat infestation in that area. And I got a real irate call from the kitchen saying, you got to get out here and fix this now. I said, what's the problem? He says, well, we're serving breakfast. And about halfway through breakfast, one of the cooks noticed the pepper was walking off the plate. They were gnats. So I had to run out. It's the only time I've ever used duct tape as a mechanical contractor to fix something immediately. So don't let it blow on the food. You put this so it just kind of blows out this way. It will capture, the hood will capture the air, but you don't want to put them so they're blowing right down on the food. Here's another special case that you have to be aware of, and that is plenum exhaust. Sometimes designers, particular architects, will design a system that has a vertical chase, and it's made out of sheetrock. And they'll want these small 50 CFM exhaust grills for a residential thing, like a apartment building or something. And they'll put an exhaust fan up here at the top, and they'll say, yeah, we just turn the fan on, and all this 50 CFMs will come out of these grills. Well, these are impossible to balance. I mean, you can try all you want, but it ain't going to work. And the reason it doesn't is because of the sheetrock leaks. A lot of general contractors, if they're never had their building tested, think when you butt two pieces of sheetrock together, you got an airtight seal. And boy, is that not true, because over time it'll crack and it'll leak. Buildings move around, so sheetrock plenums are not desirable for any use, let alone real small exhaust use. So multiple systems, you have system effect. So what happens to system effect? Anytime you'd have an air velocity and you slow it down and then speed it back up, that speeding back up takes horsepower, so that's a system effect issue. Well, here you have a problem in that you have air entering here, so the air's no velocity, so it has to gain velocity to get through this grill, and then it enters this plenum, it immediately goes back to almost zero velocity again. Not quite, but almost zero velocity again. And then it comes up, and now is entrained into this duct. Because a lot of times this ducts are real small ducts, not the same size. So now it has to collide and go to that entrance and get speeded up again. And these are very difficult, especially when they're 50 CFM. It's almost impossible. So you can get this system effect too many times. So basically, these don't work well. And the same can happen in a return plenum configuration, where you have them where they go through walls that go all the way to the deck, and they'll put a opening in the wall for the air to get to the opening, and then go to another plenum, and then to another opening of the wall. Those don't work either, because that air has to speed up and slow down, speed up and slow down. I've seen them where it sucks the sealing out near the air handler because it has to be such high pressure to make up for all those losses. And I've seen guys that have tried to clip down the ceiling to keep it from coming up. The problem is it needs a duct to go to the space one time. It should not be going from plenum space to plenum space to plenum space. And designers need to know that. It'd really be handy if designers could work on a test and balance crew for just a couple of weeks to realize that this stuff's all important for balance. Now, a duct liner can help, which just makes very little sense. I mean, it does make some sense, but it does work. So if you're going to chase it, you can't actually put a duct in. Because you're there after construction. It will work if you drop a liner down in the middle with outlets near the inlet so that there's a pressure profile right here and right here, and it will draw it in. It'll get rid of the center ones here. It'll get rid of those pressure. This doesn't look good, but it has to be close. The inlets have to be, 3 or 4 inches away. They can't be 10 feet away or 5 feet away to make this work. But it will work. It's just a plenum down there with open holes for this 50 CFM coming from each side as long as they're close. All right, that's the exhaust fan. Really short, really easy. Hope it was helpful. Thanks for being a subscribing member. I appreciate it. And good luck in your training. Have a great day. I'll see you on the next one.